Okay, so it looks like we're recording and everything. So let's go ahead and get started. Welcome to Math219. Sorry for those of you I can't see because of the big TV screen. I can't move. So we'll make do best we can in the classroom. As you can see, we're packed to the gills. And congratulations on being able to actually get into the course. We have I think, record enrollment, at least record enrollment per section this semester compared to past semesters. So I'm glad y'all were able to make it in. Okay, so first thing I have to say is we are recording. I record all of my lectures. I have for 10 years or so. And among other things, I have to point out that that means that the audio is being recorded. So technically, again, for legal purposes, I think I'm obligated to point out that this is recording. Now, I don't think it's going to pick up your voice unless perhaps if you ask a question, right, then conceivably. But there is kind of a radius on it, and it's not going to probably be recorded super well. But anyway, you've been informed. Okay. All right, so first quick thing then after the legalese. Y'all remember this whole business that I went through in the recording that y'all presumably all watched by now, the course organization thing. I'm not going to go through all this again, but I do want to hit what I consider to be the biggest point just for the sake of emphasis, and that is what this course is about, right? The learning goals for this course. This is a course about ideas and reasoning. This is what this course is about. So make sure to retain that focus. Make sure to keep that, let that guide how you think about, what you should try to understand, right? And what should be your interests and what you're looking for in this class. Now, that's not to say, of course, that you don't have to know the formulas, you don't have to know how to do the algorithms, right? Yeah, of course, there's a certain amount of rote that, execution, that, yes, sure, of course, right? But the main thing, and certainly the thing that the greatest number of students have the greatest confusion about, I'll say, is the fact that they are responsible for understanding ideas and understanding and being able to perform valid deductive mathematical reasoning. Real quick, is that window open or is that just a loud? Yeah, if it'll close, that'd be helpful. Yeah, thank you. Yeah. Okay. All right. Okay, so again, you heard me talk about that at great length on the recording. I won't repeat all that, but I think it deserves the emphasis. I'm going to move on now to some math. Now, this is kind of more context than anything else. This isn't going to be on the test, right? But just as a motivation, I do think it's a reasonable question to start off with, which is, why are we here? Why are you taking this class? Why are you taking multivariable calculus? Right? Now, I do know that for many, if not most of you, the reason you're taking multivariable calculus is because your major requires you to take multivariable calculus. I understand. Okay, so, rephrase then of the question, why does your major require that you take multivariable calculus, right? It's a very natural question. So I'm going to start off making the pitch about single variable calculus, because I think you're already probably bought in on this idea that single variable calculus is very, very important. Because derivatives and integrals, right? You've done a million things with derivatives and integrals. In general, derivatives, why do we need to understand derivatives? Because that's how we understand how things change. The world is covered with things that are changing, right? Anything that's changing, the way you keep track of how it's changing is with derivatives. So how's that for broad in application, right? That's pretty good. Let's talk about integrals. Why do we need to understand integrals? Well, what I'm going to call accumulating quantities. Anything where the whole is the sum of the parts can be computed with integrals, right? So, again, that's very, very broad. Lots of things have this feature that the whole is the sum of the parts. So, again, super duper important. And again, I think you already believe this. So I'm going to make the observation that single variable calculus, being single variable, there's only one variable. Arguably, you could interpret this as saying that this is studying functions that live on one dimension. And the thing is, that's not where we live. We live in a world that is three-dimensional. Does that make sense to everybody? Right? So right off the bat, you see there's a shortcoming with single variable calculus. Now, you can use single variable calculus to solve real three-dimensional problems sometimes. But in order for that to work out, you may have already noticed this back in your Calc 1 classes, Calc 1, Calc 2, that there were some very convenient assumptions being made, or very special circumstances that were being considered in order to solve the problem, such as, for example, the density. If you're trying to compute the amount of oil in a tank or whatever, the density depends only on one variable. Density depends only on height. Well, that's a huge assumption. That's sometimes true, but it's not to be assumed in general. I mean, in general, if you want to compute masses, density can vary. Pick up a rock, right? You break that rock up into little pieces, the density is not constant throughout the rock. And it's also not a function of just one dimension, right? So, really, what we have here is a need to recognize that what we have in the way of calculus is just not fit well for the world that we live in. So here's a couple of easy examples. Let's suppose temperature depends on position. That's an unremarkable suggestion, right? That's how it works. Temperature obviously depends on longitude and latitude, right? Watch the weather. Very dependent on location. It's also very dependent on height. You think it's cold here, try going up 20,000 feet. It's really cold up there, right? So temperature depends on position, and so perfectly plausible scenario, suppose that I'm at a given location and moving with a given velocity. How fast is temperature changing? Well, this is a multivariable problem, because as I move with this velocity, again, utterly routine scenario, right? I don't happen to be going exactly parallel to one of the axes, right? Perfectly routine scenario. X, Y, and Z are all changing. This is an unavoidably three-dimensional problem. Single variable calculus isn't going to cut it, right? And let's see, next example, let's go back to computing a math thing. Hopefully they're done. Suppose density depends on all three variables, as I have indicated in this equation here, right? So I've got a rock here, and the density varies throughout the rock. How am I going to compute the total mass of that rock, or whatever else it is that might be sitting in that region? It's tempting to say, well, I want to add up a bunch of mass. I guess an integral, maybe I'll look at one slice at a time, and the slice, maybe I can come up with a convenient formula for what the area of that slice is, and then multiply by the thickness, and then multiply the density on that slice. That's how you would have done it in a single variable calculus class, except for the fact that that assumes the density is constant on that slice. And again, in a Calc 2 class, they like to make those assumptions. In the real world, that's just not how it works. That's not how the world's set up. Right? So, okay, so the big pitch I want to make here is that, and these are what I'm going to call routine, like unsophisticated, pretty basic, actually, examples of how calculus kind of ought to work in the real world. And our single variable calculus that y'all are already good at is not sufficient. How are we doing? Pausing for questions. Everybody happy? Okay. All right. Okay. So now you may say, okay, well then surely there could just be some formulas for those unremarkable scenarios. We could just somebody can work those out and problem solve, right? So no, sadly, the applications of multivariable calculus are enormously broad, and so I have a couple of real-world-ish kind of examples. I don't have any expertise in economics, so I made up the following equation, but I do have enough awareness of economics to know that economics does have a lot of equations not entirely dissimilar from this kind of nonsense here, right? Weird algebraic equations that establish relationships between certain economic quantities. So, price, quantity, interest rate, capital, labor. I hear economists talk about these things, so maybe there's some relationship there between those, right? So if you have an economic model like this, and you want to do a little calculus, you want to understand how something's changing. For example, maybe you want to know how fast is price changing. That's a pretty useful thing to want to know. Well, a single variable calculus approach to this would say, okay, step one, solve for P. You can't. This is a transcendental equation in P, right? P is both outside of and inside of an exponential. And furthermore, there's a P cubed. You can't, practically speaking, solve for P. So how can you understand how can you take its derivative if you can't even solve it? That's a nasty little problem. Anyway, there are multivariable calculus techniques for this. This is called implicit differentiation. You've seen a kind of a single variable version of this in your Calc 1 or Calc 2 classes, presumably. The multivariable version that we're going to study will allow us to find an explicit relationship between the rate of change of price and the rate of change of these other variables. So, for example, if you can measure these rates of change here, or if you have control perhaps over, L, K, Q, and I, something along those lines. Knowing these rates will allow you to anticipate that rate. Okay. Now, I also like to point out with this example, this is a pretty good counterargument to the following tempting, mistake, I'm going to call it. A lot of people think, look, we live in a three-dimensional world. Ergo, we have no need for understanding math beyond 3 dimensions. Unless you're interested in science fiction or something like that, right? This is very tempting reasoning. It's absolute nonsense. Absolute nonsense. What we have here is math that involves 5 variables. Arguably 6 if you count t, time. These are all functions of time. Now, there's nothing sci-fi about this. This is just plain old simple economics. The prices and quantities and interest rates kind of depend on each other. Nothing weird or creepy or supernatural about this. And yet we very clearly have a situation where we need to be able to do math in 5 dimensions. And again, arguably 6, depending on how you count. Right? So anyway, FYI, now good news. I am not going to expect the unrealistic that y'all will be able to visualize 5 dimensions. Oh, no, definitely not. Don't try. It'll make your brain will melt. Right? I can't do it. I don't believe anyone else can do it. Right? So it's not that we're going to be visualizing things in 5 dimensions or 4 dimensions or anything like that, but just be aware that how to extend the understanding that we have of 3 dimensions up to being able to make reasonable interpretations in more than 3 dimensions is going to be something that's going to be important. Okay, how are we doing? What do you think? Any questions? All right, now here's some scary looking equations. Some of y'all might have seen some of these equations in the past. Don't worry about it if you don't know what these mean. We're going to talk about these, some of them, to some extent, at the very end of the course, near the very end of the course anyway. So I don't expect that you would have any previous experience with this. But this is stuff that we're going to be doing. And reasonable questions, what does all this mean? Right? What does that mean? What is that? And what is, this is crazy looking. Looks like a differential, but it's a vector. That's scary. Right? So what do these things mean is one of the first things that we're going to have to talk about. And of course, that's going to be important because, again, these equations are extremely important in physics. They're extremely important in engineering. So knowing what the things are that describe them is, of course, going to be important. Next reasonable question. These statements. How can we understand what these statements are saying? How is it that these two seemingly very different expressions are related to each other? How do we know that's true? Where'd that come from? Somebody just make that up? Is that wishful thinking? How do we know it's true? Okay. So that's something we're going to be studying and trying to make sense out of. And then next, let's see here. Why don't I zoom out just a bit here? There we go. Once we understand this statement, how does that help me? How does that help me understand electric fields? What does that tell me about electric fields? Does this give me a way of thinking, sort of intuitively understanding electric fields in a way that I would not have been able to come up with without this knowledge? Okay? So this is all really important. If you're an engineer or anything even kind of related to engineering, chemistry, anything along those lines, it's really important stuff. Okay. And by the way, and the relevant point here, multivariable calculus. All of this on the page here is multivariable calculus, right? So we're going to be understanding these very, very important things in this class. Okay, let's see here. Last example. And again, you may or may not have seen this before. If you have, cool. If you haven't, don't worry about it. Schrödinger's equation. This thing right here is one of the fundamental equations of quantum mechanics, which sounds really scary, but if you are a chemistry major, for example, right? If you want to understand chemistry, one thing you're going to have to understand is molecular bonds. And if you think about it, how do molecular bonds work? It comes from understanding the behavior of electrons. Electrons are what make chemical bonds happen. How do we understand the behavior of electrons? Well, by studying Schrödinger's equation. How do we understand Schrödinger's equation? Well, this thing right here is an object of multivariable calculus. So again, multivariable calculus is just intimately connected to, involved with what in fact is a necessary thing to really understand chemistry. So we've seen here now several examples of critical, huge, sophisticated matters that need to be understood by engineers and chemistry majors and physics majors and economists, right? So that's pretty broad. These are just the ones that I think are kind of the most dramatic and the most sort of interesting, I guess, and that betrays my background, which math and physics is kind of where I'm coming from. So I'm sure there's many more such kinds of things. But anyway, that's my answer to the question of how do we need to know, why do we need to know multivariable calculus? It's because multivariable calculus is the calculus of the real world. Single variable calculus is kind of relevant to special cases and convenient, unrealistic circumstances. We're going to make it real in this class. Is that believable? Is it everybody on board? Okay. All right. Okay. Cool. Moving along. We're going to dive in. Thus begins the material that is on the test. I'm going to start with section 1.6. We will come back to 1.1, 1.2, etc. The reason I like to start with 1.6 is because what I'm going to talk about in 1.6 is all linear algebra. By the way, for whatever it's worth, all of chapter 1 is about vectors and various things about vectors that you should already have substantial previous exposure to from your linear algebra class, presumably Math219, I think for most of you. So just to be clear, the linear algebra prerequisite for this course is a big deal. We are going to use a lot of linear algebra in this course. So if you are maybe a little rusty, or you spent the winter holiday break trying to forget linear algebra as much as possible, whatever the case may be, you do want to make sure that you're polished on what I'm going to call the basics. We're not going to do any Jordan canonical form in Math219. That's the good news, right? But we're going to do a lot of stuff with linear transformations, vectors, matrices, understanding how matrices relate to linear transformations. This kind of thing is going to be really big. So please do make sure that you are fully brushed up, polished on all of your, again, what I'm going to call basic linear algebra stuff. Okay, one other thing before I get into the math, I want to point out, and I said this in the recording, but I'm going to say it again. It's really important. I have to make tough choices that I wish I didn't have to make when it comes to deciding what to talk about in our class meetings. This is not going to be a kind of class where everything happens in class, and if you understand what happened in class, then you're good. Not so. I only get so many contact minutes. If I were to cover everything from every reasonable point of view in this entire subject, I would need 3 or 4 times the amount of contact time that I have. It's just not realistic, right? So I'm going to do a lot of picking and choosing. There are trade-offs in those tough choices. And stuff that you've already had an exposure to and is technically prerequisite to the course has to be a relatively low priority. So I am going to hit some of the linear algebra stuff. But I am going to remind you that it's kind of on you to make sure that you fill in the blanks as needed, read the book, pick up your old Math219 book, read some of that if necessary, whatever the case may be, and make sure that you fill in for all the stuff that I'm not going to have time to talk about. Okay, so for example, in section 1.6, again, a lot of linear algebra, most of this section. Make sure you study it. Make sure you're good with it. I am going to point out triangle inequality in particular. The triangle inequality is useful here and there in multivariable calculus and other places. It's really a pretty simple statement if you just look at what it says. What it says is that when you're adding 2 vectors to get a sum, the magnitude of that sum vector compared to the sums of the magnitudes of the 2 individual vectors, the green will always be less than or equal to the orange. By the way, let me apologize for the projector. The orange comes through as, I don't know what you'd call that, tan maybe? The colors just aren't very good on this projector. I'll put in a request to have them take a look at fixing that. So the green is less than or equal to the orange. The shortest distance between 2 points is the straight line distance between those 2 points. It's very believable if you really think about what it's saying. Nevertheless, that's how it's written down. It's a good thing to be aware of. Okay, here's another thing that this one I think you probably have seen. It's a point of view on how to think about matrix multiplication. Matrix multiplication, there are different ways to think about it, of course. And a lot of students, myself included, saw matrix vector multiplication in high school. And I was given a method for how to do that I thought was very handy, right? And I kind of decided to, go all in on that point of view. And, well, that's the easiest way to crank out a product, so that's how I'm going to understand it. Mistake. The best way for performing arithmetic is not necessarily the best way to understand how ideas relate to each other. It's just not. And in this case, it really isn't, right? So this whole business about dot product, row, dot, vector, and you kind of go down the rows and do all the dot products, and that gives you the elements of the product. That's a handy computational formula, which we're not going to be doing much of in this course. What we're going to be doing, again, you've heard me preach. You will continue to hear me preach on this point. We're going to be trying to understand how ideas relate to each other, right? And so much better, at least for our purposes in this class, to understand matrix vector products is to view them as being a linear combination. Specifically, it's a linear combination of the columns of the matrix. Specifically, it is the linear combination where the coefficients in that linear combination are the coordinates of the vector in question. Oh, I forgot to highlight the. Yeah, here we Okay, so this equation right here, a lot of students would look at this and say, golly, that's weird, a linear combination of vectors, that's computationally, it's harder to write down, who needs it? No, what this does, forget about computation. We'll do a little computation here and there, but that's not the focus. The focus is on ideas, and this point of view right here explains how matrices and vectors and linear combinations and columns relate to each other. And that makes this an important connection between ideas. So I want to make sure everybody has both seen this and that everybody realizes that this is going to be really handy and really much more useful for what we're doing in this class than that whole dot product business. Okay, pausing. How are we doing? Everybody happy? Okay. All right. Okay, let's talk about linearity. After all, the prereq for this class is linear algebra, right? So what is a linear transformation? Is kind of a big deal. It's very fundamental. Linearity is described by this property. A linear transformation makes this equation always work for all A and B, for all V and W. Right? Different ways to think about this. You can think about my kind of preferred way to think about it is that you can do the linear combination on the inside of the function, before you apply the function, or you can do the exact same linear combination on the outside, namely after you've applied the function, and that you get the same thing either way. To streamline the verbiage, you might say a linear transformation is a function that plays nice with linear combinations in this natural kind of way. Okay. All right, so just make sure you're good with that. There are some alternative, equivalent ways to describe linearity. Again, make sure you're comfortable with those. Presumably these have all been mentioned in Math218. Here's some examples. So, loosely, casually speaking, we say dot products are linear. Now that's a sloppy phrasing. Let me be a little bit more explicit about that. We're interested in what this thing that I'm calling P does to a vector x, and so let's look at the formula. What is it that happens to this vector x here? Well, what happens is this vector x, it gets dotted with some fixed constant vector a. That's what P is. P is the action of dotting with a constant vector A. That action, the action of dotting with a constant vector A, that's what I'm claiming is linear. Right? The fixing a vector A and then using that as a function to dot with X, that action is linear. That makes sense to everybody? Okay. So importantly, when I say that P is linear, you got to keep in mind, linear is a statement about a function, not an operation. I'm not saying dot product itself is linear. I'm saying that this expression, if you interpret appropriately as a function, that A is constant and that the action is happening to, the object of this action is the vector X. As a function of X, this is linear. So a little subtlety in there. Everybody okay with that? Okay. All right, let's see here. Cross product, likewise, also linear. And again, a little sloppy to say that cross product is linear. We have to be precise about what's a function of what, right? But again, in the sense that X is something that we're doing stuff to, and in the sense that what we're doing to it is that we're crossing it with a fixed vector A, that action of crossing with a fixed vector A is linear. Okay. All right, same thing, different operator. Okay, here's a weird one. I kind of referenced this example, you may recall, in the organizational lecture. Throws students a little bit for a loop. This function D is linear. Now, again, you got to be careful in how you interpret this statement. it is tempting to say, well, D apparently is determinate, and so I guess this is claiming that determinant is linear. Absolutely not what this is saying. Determinant acts on matrices. I am not claiming that if you add two matrices, then the determinants add. I'm absolutely not claiming that at all. That's not what this statement says. D and determinant are not the same things. Let's see here. Where's my button? There it is. Okay, so determinant acts on matrices. There's a matrix, for example, that determinant applies to. D is not. D is everything other than this x here that we're plugging in. That is, the input to our function. D is the act of taking a determinant after you already make these fixed given input vectors r1 through rn minus 1. Make these the first n minus 1 rows. And then the input vector x you fill in only as that last row, and then you take the determinant. Right? So make sure not to conflate the purple thing with this blue-ish looking thing. Right? The purple function acts on matrices. This dark blue function acts on vectors. It's this dark blue function, D, that we're claiming is linear. So now this is something that, again, ideally should have been covered in a linear algebra course. This, by the way, sometimes referred to as the multilinearity of determinant. It's a really useful thing to understand about determinants. You may recall at some point in your class how do you compute determinants? And there's this clever observation. If you look at row reductions, right, you can just keep track of how the determinant changes as you go down through a row reduction, and then you can kind of work backwards to find the original determinant. Very clever. Fundamentally based on this fact that D is linear. In other words, that determinant is multilinear. In other words, that determinant, thought of as a function of one row at a time, is linear. How we doing? Okay. All right. It's confusing. It's definitely a weird example. Give yourself the time necessary to make sure that you're comfortable with this idea. It's, I think, a really nice exercise in making sure that you have a good sense for what linearity means. Okay, moving along. Huge theorem. Really important theorem. As I mentioned already, we're going to be understanding linear transformations, what I like to call Euclidean linear transformations. Linear transformations where the domain and the target are both Euclidean spaces, Rn to Rm, for example. Euclidean linear transformations, by the way, again, hugely important. We are going to be doing all of this entire course in Euclidean spaces, Rn and Rm. Linear transformations are a really big deal in Rn and Rm. So understanding how to represent them in a most convenient way possible is a really big deal, and here's what the theorem says. Every such linear transformation, in some sense, can be thought of as a matrix. All linear transformations can be thought of as a matrix, and by which I mean there's always going to exist a matrix. Oh, missed. Let me try that again. There's always going to exist a matrix such that our linear transformation can be computed by multiplication by that matrix. Hope that looks familiar. Again, this is a really important fact in linear algebra. So I want to remind you how this result is shown. Now this is an if and only if. If you give me a linear transformation, there's a corresponding matrix. Likewise, if you give me a matrix, then this is a linear transformation. Proving that first fact, proving that every function of this form is a linear transformation, is just a matter of doing it. Just look at the definition of a linear transformation. Take this formula, explicitly crank out from the definition and confirm that, yeah, sure, as required, that works. Right? So it's what I call direct computation. It's a good exercise, by the way. You want to make sure that you can do this. By the way, another procedural point, it will be regularly the case, again, tough choices and all that, that I'm going to leave as an exercise for y'all to think through on your own. Right? Now, that's not something you're going to submit. You're not going to turn it in as part of the homework or anything like that unless I've forgotten and it actually is a homework exercise. I don't remember. I don't think it is. Anyway, I'm not presuming that you will turn it in. But I do strongly advise in class, in the very many occasions when I say, hey, this is a nice exercise, make sure you can do that. That's an insight into what I think is important. Right? And things that I think are important, two useful things for y'all. It probably is. Right? It'll be a good instructive experience. But also things I think are important inadvertently, with no intention on my part, have in the past shown up on exams because I think it's important. Right? So anyway, for your consideration there. But I do think this is a good exercise. All right. So let's, though, look at the other half. How do we show that every linear transformation can be expressed with a matrix? That's a trickier side. Oh, whoa, I hit the wrong button there. The trickier side of this. If all I know is that I have a linear transformation, how do I know that there's going to be a matrix that does what I want it to do? Where does the matrix even come from? And here's the tricky move. Keep in mind, we know by assumption that we have a linear transformation. That means that when I look at x as a linear combination in the usual way, standard basis vectors and all that, linearity allows me to take a linear combination on the inside and rewrite that as a linear combination on the outside, right? So this is the important first step right here. And so linearity is exactly what makes this possible. And then I'm just going to make a clever choice. By the way, I mean, don't be intimidated by the clever choice here. It's this happened to me when I was going through this the first time. That this kind of thing anyway, where the professor says, I'm going to choose something out of thin air, and I just thought, wow, I don't have the intuition apparently to be good at this stuff, because I never would have occurred to me to just make up this formula, right? And to be clear, it did not just occur to my professor either, just like it didn't just occur to me here. I'm doing this because I'm a mathematician and I've done a whole bunch of stuff with this and I've seen this a million times and I kind of know how the story's going to end, and so this is not a spontaneous choice that I've made, right? This is something that was carefully planned and first figured out by very, very clever people long ago, and everyone since has been copying them. Right? So anyway, don't let that freak you out. Okay. All right, so we're going to make this choice, and now keep in mind we've already got this equation. So if I make this choice here, let's see here, colors. If I choose to make the columns of my matrix be T of E1, T of E2, T of E3, etc., all the way through T of En. If I make that choice, then look what happens down here in this equation that I'd already established. And I'd already established that T of X is X1, T of E1, blah, 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 all this in purple here. But just having decided to generate my matrix this way, I get a linear combination of the columns of my matrix with the coefficients of the vector as my coefficients of the linear combination. I get what is, as we just discussed a few minutes ago, kind of the definition of a matrix product. And thus, as desired, there we go. T of X equals AX as it's supposed to be. Everybody see how that works? It's very clever. So now I want to go back to the very beginning of this page real quick and talk about, again, what this theorem says. Again, the theorem's super duper important. Every linear transformation can be thought of as being a matrix. That's tremendously important. The other tremendously important thing about this theorem is actually part of the proof. And that is, while the theorem only says that this matrix exists, the proof is what tells us the formula for this matrix. Right? Making the argument, making the pieces fit together is what allows me to have a sort of a plug and chug formula. If you want to find the matrix that represents a linear transformation, okay, yeah, here it is. That's the formula. Enjoy. I hope this is useful. All you have to do is take your standard basis vectors, E1 through En, plug them into your linear transformation to see what happens, and make them the columns of your matrix. E1 through En are really easy vectors. There's only N of them. It's not that many, typically 3, sometimes 2. Right? So it's a couple of convenient calculations. Make those the columns. Bam, you've got your matrix. So again, really, really important fact. And make sure that you remember this really important fact. Okay. All right. Last thing I want to point out in this section anyway is this is another thing that, again, in an ideal world would have been covered in linear algebra class. I think it should have been. I don't want to, anyway. But I want to be able to assume, so I'm going to state here for our use this theorem that says that when you multiply matrices, that corresponds to composing linear transformations. So in other words, if you have a couple of linear transformations, S and T, now they are linear transformations, and so there are matrices A and B that represent them, per our theorem that we just established. The act of multiplying the matrices that represent the transformations results in a new matrix that literally represents the composition of the two transformations that we had in the first place. So also very useful, comes up surprisingly often, and make sure you're comfortable with that. Yeah?
Can you just go over briefly what a composition is?
Yeah, composition's where you plug the output from the one into the input to the other. So in particular, S composed T of X is S of T of X. So you're going to take this X. The first thing you're going to do is you're going to plug it into the T function and see what comes out. Whatever it is that comes out, that's what you're going to then plug into the S function. And yeah, right.
Okay, thank you so much.
Yeah, no worries. How are we doing? Anybody else? Okay. All right. Yeah, cool. Okay, so that's section 1.6. We're going to move on now to section 1.1. Again, I did them a little bit out of order. I'm going to say very, very little about section 1.1. I believe y'all should already be experts at everything that's in 1.1. Now, again, reminder, just because I believe it doesn't mean you should assume it, right? So you should go through, make sure to at least flip through, kind of scan, and make sure that you truly do feel really good with everything in 1.1. If you find something where you're a little, wait, what's going on there? Make sure to read that, make sure to solidify, make sure that you're strong on all that stuff. Of course, by the way, I hope this is always clear, if you have any questions about stuff you find in the book you can't resolve for yourself, seek help, right? There's so many different sources of help. You've got office hours, you got my office hours, you've got the other two professors' office hours. You're perfectly welcome at those as well. There's the help room. Oh, did I believe yeah. Okay, so it's coming back to me. I put the link to the help room on the website, but I think I did that after I distributed the website. So you may, or depending on when you looked at the class website, the course website, you may or may not have seen that. But we do have an operating help room for this course. It operates for something like 10 hours a week. It's really convenient, right? You just show up, no appointment necessary, ask your question, right? So please make sure to make appropriate use of that. Again, study partners, I'm a big fan, right? I think, if you have a question, ask a friend. It's a really great way to get an answer, right? And then if it's not satisfying, well, then you go to the help room or you come to office hours, whatever. Okay, so just a couple of quickie things I'm going to say about 1.1. First of all, the book uses this notation where they use bold to indicate that something is a vector. I think that's a little rude, frankly, because they're doing stuff that students reading the book who are writing with a pen can't conveniently do. I think that's mean, right? So I try to avoid that notation myself, but I apologize. It is actually pretty common notation, right? So I like to always use the vector hat, that little arrow that you put over it, like so, because that's something that you can effortlessly with a pen write. Okay, all right, so that's about half of what I'm going to say on section 1.1. The other thing I'm going to point out, I'm just not a fan of this notation right here. It's not wrong. There's nothing bad about it, I guess, as a way to represent this vector. Right? But there is something kind of weird about why we would concoct an oddball notation for something that we already have a perfectly good notation for. It's P2 minus P1. Pretty straightforward. Keep in mind now that there's this natural correspondence between points and vectors. Every point represents a vector. Vectors represent points. And specifically, for example, let's see, I'm trying to avoid the colors that don't show up well. P1 can be thought of as that point, but it can also be thought of as this vector. And likewise, P2 can be thought of as this point, but it can also be thought of as that vector. And given that we have this existing, truly fundamental idea that there's this natural correspondence between points and vectors, we already have a notation for this thing. The notation is that it's P2 minus P1. What's the difference between this notation and that? What does this bring into the table, right, that we don't already have here? In fact, I'll point out this notation is bad in a certain way that it hides important reality. It hides the fact that there is algebra involved here. We like algebra. Algebra is our friend. You can't use the algebra if you don't see the algebra. So anyway, this is one of my little personal pet peeve. Everybody's got their little oddities. So I'm just going to put a frowny face next to that. Again, it's not wrong, but I don't see the advantage of that. So anyway, heads up. This is in the book. You're going to find that I only write this down for the purpose of making fun of it. Okay. Alrighty, that's section 1.1. Got that done. And now we're not going to have much time to get into 1.2, but I will say just a couple of quick things. I want to define what a parameterization is. It's going to be a really useful thing in this course. When we get, for example, into chapters 6 and 7, that's kind of the culminating chapters, the big finish, the climactic, sort of what everything in the course is leading up to. Parameterizations are going to be indispensably helpful. So we're going to talk about parameterizations throughout the course. When even in cases where, we could have gone a different way with it because we're trying to lay groundwork for what's going to be so important in chapters 6 and 7. So what is it? Parameterization is a function where you have position as a function of a single parameter. Thus the term parameterization. I like to think of that single parameter as being time, because if you have position as a function of time, that just describes motion. right? I like to think of that as that's the process of tracing out your curve. So a parameterization can literally be thought of as drawing what we call your parametric curve. So as a quick, let's see, wait a second. Do we have, no, we're out of time. Okay, so I'm going to draw the line right there. That's where we finished for today. I'll record that on the website, by the way. Keep in mind the class website, class schedule. In these two cells right here, I'm going to indicate where we just finished. And see y'all on Friday. Have a good one.